we did now a problem where we used Coulomb's law looking at one dimension. So I want us to quickly do this one together for the purpose of now fully understanding how we can go about treating a two-dimension problem, going about now ensuring that we are able now to answer even if we are given a two-dimension problem. So this one I'm just going to say at 15.1, it's easy 2 marks because now it's a law, and remember we must get all our definitions right. And then now at 15.2, I will write here 15.2. It says now two small spheres x and y carrying charges of plus 6 multiplied by 10 to negative 6 coulombs and plus 8 multiplied by 10 to negative 6 respectively are placed now 0.2 meters apart in air. Calculate now the magnitude of the electrostatic force experienced by X. This should be now easy to do because I can easily say I have F, which is K Q1 Q2 divided by R squared, 9 multiplied by 10 to power positive 9. And now I have my charge, which is 6 multiplied by 10 to negative 6. And I have 8 multiplied by 10 to power negative 6. And then divided now by the distance between the two is 0.2 meters squared. And I find my final answer as something like, let me write it here, 10.8 newtons. So this one, I believe each and every one of us should be in a position of getting the 4 marks. So it's 1 for the formula, 1 for the substitution, 1 for R squared, as well as now for the final answer. So this one, all of us and each and every one of us must be in a position of getting it right. So I'm not interested in that one because majority of us are in a position of doing it the right way. So now let's go to 15.3. It says now a third sphere of Z of an unknown negative charge. So all I know is Z is now having a negative charge, is now placed at a distance of 0.3 meters below sphere Y in such a way that the line joining the charged spheres X and Y is perpendicular to the line joining charged spheres Y and Z as shown in the diagram alongside. Draw a vector diagram showing the directions of the electrostatic forces and the net force experienced by the charge Y due to the presence of X and Y. Remember, we said now when we work with charges placed in two dimensions, we always say our reference charge will be now the charge at the center. The charge now where the two meets X and Y, and now Y and Z. So I did not even have to read the full question in terms of understanding exactly what they want, but automatically, once I saw that I am working with 2D charges or charges placed in a two-dimension, automatically I know that my center charge must be now what? Must be my reference charge. So we must draw a free body diagram for that. Let me get my line. So what will be the influence of X on Y? Because now X and Y are both positive, it means now Y and X will repel each other. So for them to repel, it means the force of X on Y must be in this direction. And then now I must have a force of Z on Y. But I know that now Z is negative and Y is positive. So it means Y will move towards Z. So that will be now a force of attraction between the two. So if it's a force of attraction, it basically says Y will move towards Z and Z will move towards Y. So this allows me now to have another force that is now at the 90 degrees. Then we move it again closer. Something like that. Then I'm going to have my net force. Remember, it says also indicate the net force experienced by Y. So my net force, I know it will always now be between the two forces thereof. So I can easily move this one closer so that I have a nice 90 degrees. So I am now in a position of labeling it. Remember, it's not a vector diagram if it does not show all the forces. So I'm going to say now this must be F of X on Y, and this must be F now of Z on Y, and then this must be my F net. So by so doing, I will be now in a position of ensuring that I get the full 3 marks. So it's one of those questions that in most cases we tend to ignore. But when you look at it, it's now part of the exam. It's now part of what is the assessment. So it basically says I will get one there, and this will now give me my 3 marks. So I just wanted to show you with this question to say everything is possible. Everything that we work with is in a position of now the examiner can ask anything and everything related now to Coulomb's law. So we also need now to be able to accumulate this maximum marks. So I'm at 15.4. I believe we are still together. I'm at 15.4. So at 15.4, they say now, the magnitude of the net electrostatic force experienced by charge Y is 15.2 newtons. Calculate the charge on sphere Z. And remember, we said sphere Z is a negative charge. So let's see if we can be able to solve this particular problem. But now, what is it that I have? I am given F net, which is equals to 15.20 Newton. So it basically says, I calculated earlier at 15.2 the influence or the magnitude of X on Y. So that force was something like 10.8 newtons. That is what we calculated. So it basically says to me, if I can use now the Pythagoras Theorem, remember, once I have now angles in charges in 2 dimensions, it becomes easy for me now to apply Pythagoras Theorem. So I'm going to say now F net squared is equals to F net squared is equals to F of XY squared plus now F of ZY squared. So this is just now the application of the Pythagoras Theorem. But what is it that I have? I have now that F net is 15.20 squared I know f of xy is now 10,8 squared. Now I am looking to calculate for fzy. So what is it that I am going to get? I am going to get the value of fzy, of which I calculated, and I found it to be something like 10,696. So after doing everything squared, I get now my fzy, which is equals to 10,696 newtons. But now this is not the answer to the particular problem that we are asked. So I'm going to say now, can I apply Coulomb's law? Yes, I can apply Coulomb's law. And then the only thing that I must do here is now substitution of the values I have. So I have now this as 10,696, which is equals to 9 multiplied by 10 to power 9. And then what is the charge on y? It's 8 multiplied by 10, negative 6. And then I am looking now for qz. Then I divide now what is the distance between y and z. I find it as 0,3 squared. Then doing the mathematics, I will eventually find now my Q2 or QZ is equals to 1,34 multiplied by 10 to negative 5 coulombs, negative 5 coulombs. I see we have something in the chat. Like your answer for 15.4, it's 7,7 multiplied by 10 to negative 6. That is incorrect because now maybe you missed a step somewhere. Kindly go back and check. But now the answer that I got here, it's now QZ is equals to 1,34 multiplied by 10 to negative 6. Or negative 5 coulombs. So that is now the answer I got. Kindly check me on that and verify my calculations as well. But I believe everything that I have done should be clear. The only problem now was maybe now not knowing exactly where to start. The questions that we came across earlier were emphasizing that calculate Fnet. But in this case, Fnet now was given to us. And when Fnet was given to us, it means now we had to start with the Pythagoras Theorem, get now the f of zy, because that we did not have. Once I have that, now I applied Coulomb's law in order for me to get my maximum marks. So I'm going to give you a timer of maybe 30 seconds for you to digest it, and then I will move to another section of the day. So if you have something to say, kindly raise your hand or even say something in the chat. If it's clear, then I will move on. Thank you very much. I didn't get any messages. Everything is fine in the chat, and I didn't get any hands being raised. So it basically says you fully understand how to approach this particular problem. So my intention was for me now to show you that we can still get questions where we need now to apply the 2 dimensions. So I didn't want to move on to electric field before I can ensure that we are happy with everything that is now Coulomb's law related. So now for today, or the key concepts that we need to attend to is going to be the electric field. So now, by now, most of you have seen how I start introducing new concepts. So with electric field, we are only building on top of what we already know from Coulomb's law, because we'll still be working with charges. We'll still be in a position now of applying and drawing graphs and everything that is science related. So me starting the introduction of electric field, I'm going to say, let me have my center, and in this center I have everything that is related to the electric field. I am going to start now with the first one, which is the very same electric field. What do I need to know with electric field? It's very easy. I need to know the definition of an electric field. So a definition of an electric field is defined as a region of space in which an electric charge experiences a force, or not forces, but a force. So we know that now we have this region or this space, but in that space, what is it that is happening in that space? We have now a charge, and that charge is experiencing a force. But if it's experiencing a force, it basically says to me, once I have a force, an electric field now must be a vector quantity. This is very key. If it's a vector quantity, it says to me it must always have now direction and magnitude. So because of this, we can easily associate the force with the electric field. So basically, the electric field will take now the direction of the force. I am going to explain that in simple formula, and the simple formula is E is equals to F over Q. And we know that now Q is a charge measured in coulombs, and it's a scalar quantity. And we have now the force measured now in newtons, which is a vector quantity. So basically, the vector nature of the electric field is influenced by the force. So even if I am going to draw a free body diagram of the electric field, it becomes easy because I can only focus now on the force. So basically, the direction of the force influences the direction of the electric field. And then we move now to number 2. Number 2 is electric field at a point. Electric field at a point. So electric field at a point. We also need now to know the definition thereof. What is the definition? The definition is the electric field at a point is the electrostatic force experienced by or experienced per unit positive charge placed at that point. I'm going to write it down and we scrutinize it further. We have a charge at a specific point, and that charge is now experiencing a force. That is what it basically says. So we say now the electric field at a point, the electric field at a point is the electrostatic force, is the electrostatic force experienced per unit positive charge at that point. Remember, this definition is a definition as per the exam guideline. So if you do not give the exact same definition, you're going to lose a lot of marks for that. If you do not now define in terms of the weight at that point, the weight at that point, we are also going to lose a mark, because what is it that we are looking for? We are looking for a difference between an electric field and electric field at a point. So the electric field at a point is the electrostatic force experienced per unit positive charge at that point. So it basically says my point charge or point of reference. So my point charge, I must add it here, and maybe write it in red and say point charge will always be positive. The reference charge or the point charge will always be positive. Fully agree. So can we do something about the whole of this information? Yes, we can. We will be now in a position to say, let's further extend it to number 3, which is now the direction of the electric field. Direction of the electric field. Direction of the electric field. We also need now to know the definition of that. If you haven't been asked it, expect it now in the near future, because it's one of the terms or one of the definitions that each and every one of us must be able to follow and know. So it basically says now the direction of the electric field at a point. So the direction of the electric field at a point is the direction that a positive test charge, that a positive test charge will move if placed at that point, will move if placed at that point. What does this basically say? It says now the direction of the field will be influenced by the positive test charge. So the test charge will always be positive. Hence, I did say now the point charge will always be positive. In this case, it's a test charge. So we either call it now a point charge, or we can even further call it a positive test charge. So a positive test charge will now move if placed at that point. If placed at that point. So these are just key definitions of which each and every one of us must be able to know and fully understand. So this allows us to be in a position of saying, regardless of what the examiner is asking, regardless of the definition that I need now to give, I will fully be in a position of exactly understanding what is it that I must do. So I'm going to duplicate this and then clean the other side, because I want to add something also to it. So I'm going to duplicate and then remove few things, because I need now to expand the chart thereof. So let me move and duplicate. Then it will allow me now some space for me to add a few things that I want us now to look into. So while we wait for the computer to respond, I hope so far everything is fine and we are in a position of fully understanding how to approach electric field. It's not a complex concept. It's just a concept that allows us now to understand the link between electric field and Coulomb's law. So let me remove this. And I'm going also to remove this. Okay. So going to remove this. We don't need. Then I can further add now number 4. So what is number 4? Number 4 is electric field equations. So with electric field equations, we have E is equals to KQ over R squared. And then we have E is equals to F over Q. And I added N is equals to N is equals to Q over QE. So these are the equations that we are exposed to, or that we are going to use. But what does it necessarily mean in terms of the SI unit? So regardless of what I use or which equation I am focusing on, the SI unit will remain Newton per Coulomb. Even though, if you check the first equation, you have E is equals to KQ over R squared. The SI unit will still be Newton per Coulomb. Newton per Coulomb basically now comes from where? From the second equation, where we know that F it's measured in newtons, and then Q it's measured in coulombs. So now this will now be Newton per Coulomb, regardless of what you use. The third equation has the number of electrons, Q over QE, which is the number of electrons. So this is an equation that I want us not to forget, because it works now throughout the whole entire topic. But what does this basically say as a hint now for me? It says I can only use these equations, when working with one charge only. So you can only choose this equation and apply it for a specific charge. So a point charge or a test charge will always be given. So this allows us now to use only one specific charge. So we cannot apply Coulomb's law and want to calculate electric field. You cannot now apply Coulomb's law and now think that you will be able to use these specific equations. So once we get into this position, it means now if you are bound to use Coulomb's law, it is going to be a multi-step. Multi-step means now what? Take information from Coulomb's law and then substitute into the electric field equation. So when can I use the first equation? I can only use the first equation provided that I am given now the distance between the point charge and the specific charge that I am working with. So if that is not given, then it basically says the challenge will be that I need now some form of a distance such that I can use the first equation. But now the second equation becomes easy because now I have now what? I have a force and a charge only. So this brings me now to this other section here, of which it's number 5. And number 5 is basically just the graphs. So if it's the graphs from the two equations that we have, especially now looking at the first one, where I am going now to draw E versus Q, looking at the first equation, versus Q. It's going to be easy for me to do it because now I will have my line here and I will know that I'm going to have a straight line thereof. This will be my E and then this will be my Q, looking at the first equation. So I must say we are referring to E K Q over R squared. Remember, K is a proportionality constant. So I cannot now be looking at the second equation, because if I use now the second equation, I am not going to have the proportionality constant that allows me to be in a position of getting straight lines and the best fit graphs. So the second one is E versus 1 over r squared. So I'm going to draw the line again, and this now will be so let's look into the equation. What happens now, the relationship between E and r squared. The relationship between E and r squared is that now E and r squared are inversely proportional to one another. So if they are inversely proportional to one another, then it basically says I must have now the increments of r increasing and E now decreasing. So this will allow me now to draw a correct graph because of I fully understand the relationship between the two. So I'm just going to remove this and draw the right graph for you guys. Then I'm going to just say this should be now something of this nature, and this is r squared, and this is E. And then I will draw for C, which is now E versus, or the very same one, we can just say, or if we draw now for the r squared, we can easily say this one is for r squared, and then we can have the same one, which is a straight line, but this is now E over 1 over r squared. So in the near future, expect a lot of questions where we address the graphs. Expect now to be in a position of fully understanding how to use each and every graph that you are exposed to. So this will now help you to fully understand the relationship thereof. Because now with graphs, like I did say earlier on, it's always a challenge. So now with graphs, it's always a challenge in terms of how each and every one of us interpret the specific graphs. So I'm going to give you 30 seconds to analyze and digest the information that is given before I can now introduce another different concept. So let me give you your timer. And this will be 30 seconds. And then I can see Manuku, your hand is up. So Manuku.
Evening, sir.
Evening, Manuku.
Sir, I want to ask according to B of E versus 1 over r squared. What's the difference between those two graphs?
Okay.
Because what I understand is that electric field is inversely proportional to distance. So I think that the most regularly used is that the second one. So
okay.
I don't understand the difference between them.
Okay, the only difference is check here. Let me get my highlighter. Check here, ne? This one, sorry, highlighter. This one here, we are drawing for r squared. So r squared is the one that is now inversely proportional to E. But 1 over r squared, it's not inversely proportional. It's directly proportional. Hence, we will be in a position of getting the straight line. So kindly check here that we are drawing now for 1 over r squared. So it basically says we are taking now the inverse of 1 over r squared. So basically we are making r squared now to be directly proportional if we take the inverse of 1 over r squared. So the relationship between the two is basically the same. It's just an issue of which one are you drawing. If you are drawing for E and r squared, you will get this line that shows now they are inversely proportional. But now if you are drawing for an inverse of r squared, then you will definitely get a straight line. That is the difference between the two. Are you fine,
Okay,
Manu?
sir, I get it now.
Thank you very much.
Yes, sir.
Okay, so let me give other guys their 30 seconds and then for you to digest this. Thank you very much. I didn't see any hands or any comments in the chat, so I believe each and every one of us is fine. So I'm going to add another slide. I don't want to copy this. I just want to add. Then I will be in a position of starting something fresh. That is now number 6. So at number 6, it's electric field patterns. So with electric field patterns, be on the lookout at something that we need to know. It's usually 2, 3, 4 marks, not 4, usually a maximum of 3. So for the rules of drawing the electric fields, I would like you now to page into 241 of your book 1 Olivier. 241 book 1 Olivier. That's the red book or theory and workbook on page 241. I'm just going to read them out to save us time. It basically says now, properties of electric field lines. Okay, let me write it down to say refer to page 241 of book 1 Olivier. Very, very important. It will save us a lot of time. It will save us a lot of time. So book 1 Olivier. So I'm reading from there. Properties, I'm at number 2. Properties of electrical field lines. They originate and end perpendicularly to the surface of the charged object. They can never cross or touch each other. They are more dense or close to each other where the field is the strongest and least dense from each other. Their direction is according to the convention from positively charged object to the negatively charged object. They surround the charged object in 3 dimensions. We only draw a few lines on one plane. There is a uniform field between 2 positively charged parallel plates. That is now what we are not interested into. So if you check number 1 up to number 5, It's basically the key rules that we are looking for. So in an exam, if one of the rules is being violated, we omit 1 mark. So the rule is they originate and end perpendicularly to the surface of the object. They can never touch or cross each other. Their direction is according to the convention from positively charged object to the negatively charged object. So they always move away from the positive charge. The negative charge will always now receive, the charges will move now into the negative charge. So at number 1 there, everything has been represented accordingly. But I'm interested in the electrical field around a positive charge, electric field around a negative charge, and electric field of 2 equal but opposite charges. And now the ones for repulsion, so we should also be in a position of drawing for that. So that is very, very key in terms of the electric field. So this is easy marks that we are going to, all of us, be in a position of getting, but we need now to know exactly what are the rules, because now once they touch, we penalize. Once they cross, we penalize. If they do not touch the charge or the sphere, we also penalize. So these are key things that I want us to look into when we draw now our electric field patterns. So moving on, I must maybe now explain or give you exam tips on how to approach. But when you look at it, I don't think we can do that. Let's look into the question now that is given, or I have a simple question that I want us to look into as an example. As an example, they say now I have Q1, Q2, and I have my point charge P. I am told now the distance here is 6 centimeters. It's 6 centimeters, and the distance here is 6 centimeters as well. And I am given that now this is plus 2 microcoulombs, and now this is plus 12 microcoulombs, and now P is just a positive point charge. So I want inputs from you guys. And the question says, calculate the net electric field acting on P due to Q1 and Q2. So the question is specific. They want us to calculate the net electric field strength experienced now by P due to Q1 and Q2. I'm going to ask you to raise your hand for someone to share how best can you go about this. Jerry, your hand is up. where can we start? What is the best way of approaching this particular question? Yes, let me start with Jerry. Have you seen you are noted? Jerry?
Teacher, the best way to subcon this kind of problem is to start with a free body diagram.
Free body diagram. Okay, thank you. Ntabiseng Chabalala, where do we start? What will be your best approach to this?
Nanta, my best approach would also use the free body diagram and to convert the 6 centimeters into meters.
Thank you very much. Thank you very much, Ntabiseng. I think that's enough input. Generally, because we are working with a vector quantity, the best thing to do, and which is now in terms of the force, so we must now first draw a free body diagram for us to be able to understand exactly how are we going to get our E net. So as the question says, it will always be easy provided that we draw the correct free body diagram. So this is what I said earlier on. I said electric field is a region of space in which an electric charge experiences a force, and it's a vector quantity. So what is it that influences the electric field to be a vector quantity? I said it must be the force. So the force is giving us now a vector nature of the electric field. So some people will say, I'm drawing for an electric field, it's fine. You will still get the same thing. Some people will say, I'm drawing now for the forces, it's fine. You will still get the same thing because the force is the one that influences the vector nature of the electric field. I repeat, the force because of its vector nature is the one that influences the vector nature of the electric field. So if now the force is to the right, the electric field should be to the right. The reason for that is force influences the vector nature of the electric field. Hence, I wanted us to understand this fully. So when coming to this type of equation, it becomes easy for me to understand and draw the correct free body diagram or whatever question might want in terms of understanding this fully. So it becomes easy because already it's things that I know from where? From the Coulomb's law. I did say also that now the reference charge will always be positive. So the direction of the electric field at a point is now the direction that a positive test charge. So already I know that now P must be positive. So already I am in a position of drawing the correct free body diagram. So whether you draw for electric field, it's fine. You'll still get the same thing. Whether you draw for the force diagram, you will still get the same thing. So I am going to draw now for the forces acting on P. The question is, what will be the influence of Q2 on P? It's positive, so it means P will move now away with a longer force between that. So this will be E of 2 on P. And what will now be the influence of Q1 on Q2, or so on P? Because of now the distance between the two becomes now 12 centimeters, it means I am going to get a smaller electric field here, which is now E of what? Of 1 on P. So I hope you guys got the same thing as me. So by so doing, it basically says I am in a position now of calculating. So how am I going to calculate for this? I am having two vectors. So it basically says I must use now the equation of an electric field at least 2 times. It's as simple as that. So I'm going to do this one as an example. Then we will try to do the second one together. So this now becomes easy because it's going to assist me in terms of the choice of direction. This is going to assist me such that now I know where to plus and where to minus. So Jerry was right to say free body diagram. Ntabising was also right to say free body diagram. So as long as you cannot draw the correct free body diagram, there is no way you will be in a good position of getting the E-net correct. So let's just remove this quickly and now do my calculations quite fast. Kindly assist me because you guys are somehow faster than me. So I'm going to calculate E of 1P. So this is now K Q over R squared. So this is 9 multiplied by 10 to power 9. And then I am told Q1 is 2 multiplied by 10 to negative 6, divided now by 12 centimeter. 12 centimeter is 12 divided by 100. 12 divided by 100. We should be able to do that, all of us, to power 2. Then I'm going to wait for the answer for you guys. And then I can do now E of 2 on P. This is just now K Q R squared, 9 multiplied by 10 to power 9. And then I am told Q2 is 12 multiplied by 10 to negative 6, divided now by 0, 0.6. Let me check. 6 divided by 100 is 0, 0.06 squared is equals to Newton per coulomb. So let me check what's the answer for the first one. The answer for the first one is 9 exponent. Let me quickly do it because you guys are not assisting. 9 exponent 9, and then 2 exponent negative 6, divided now by 0, 0.12 squared. Something like 125,000. And then for this one, it's 9 exponent 9, 12 exponent negative 6, divided by 0, 0.06 squared. So this is, we take it to scientific notation, 7, 3. So it's 3 multiplied by 10 to power 7. To power 7, 100%. Then let me check. Thank you very much. Then E-net is equals to E1P plus E2P. So now this becomes easy in terms of the direction I can just say everything moving into that direction must be positive. So I'm going to have 1 to 500 plus now 3 multiplied by 10 to power 7, which is just equals to plus 1250000 is equals to something like 3,13 multiplied by 10 to power 7. And that's the final answer. So that's the final answer. So 3,3,1 or 13 multiplied by 10 to power 7, then newtons per coulomb. Now, because it's a vector quantity, you must also give now the direction for that. So the direction for that will be to the right. If I am given east and west, then it will be to the east. So it becomes easy once you understand the concepts of Coulomb's law. It becomes easy when you start now understanding the concepts of how to use the specific calculations or formulas thereof. So the final answer is 3,13 multiplied by 10 to power 7 Newton per coulomb. So I am going to give you, I see most of you found it right or got it right, and then others said east, others said right. There is no problem with that, because now in this case we are not given any direction in terms of east, west, or right or left. But now I must say, in an exam, they will tell you now that this is east and this is west, and then this is north, and then this is south. That they will tell you. So you can only use east and west provided you are told. But now if they decide now to use right and left, then you can only say right or left, nothing more, nothing less. If we have given you left and right, you cannot be in a position of saying now east. If we give you east and west, you cannot say right or left. It must be east, because the final answer will be that. So I'm going to give you 30 seconds to digest this one. And if you are happy with it, then we can move on. Get your calculators and formula sheets ready, because the next one is entirely up to you. Any hands? Any comments in the chat? Thank you very much. Then it says everyone is happy with this one. So the next one is entirely onto you, and then we'll explain it in detail. I'm going to give you something like be quick with it. I'm going to give you something like 7 minutes on this one. Let's go. Send your answers into the chat. And remember, I'm going to choose anyone to kindly assist and help and explain this in detail. Thank you very much. Majority of the answers I saw for 4.1, most of us got it right, and some for 4.2, and then 4.4. Unfortunately, the answers I received were not correct. So let's see what seems to be the challenge thereof. I'm going to start with 4.1 quickly. So for 4.1, we are told two identical spheres, M and N, are placed in insulating stands. They are brought into contact. Very key. So it means they touched. Let me check the answer here. Busiso Makoba, not so right. Let me explain, and then we'll see or check the mistakes we made. So now we are told that, and a charged rod is brought near the sphere M. When the spheres are separated, it is found that 5 multiplied by 10 to the power 6 electrons were transferred from M to sphere N. So what is the net charge on the sphere N after separation? This one will be easy to do because we are given the number of electrons, and we have now the charge of an electron, which is a constant. That one will be easy to do. So, but what is the trick here? The trick is the two spheres were brought into contact with each other. So if they were brought into contact with each other, it means now their net charge for both M and N will be the same. But the fact that M is the one that is now losing electrons, it means that M must be now more positive. So I'm going to do it now again quickly. So it basically says now, because M is the one that is losing the electrons or transferred from, it means M becomes now more positive. That is the catch. So now N Q over QE, the number of electrons is 5 multiplied by 10 to power 6. We want to know what is the charge, minus 1,6 multiplied by 10 to negative 19. Then we do the mathematics, and then Q is just negative 8 multiplied by 10 to negative 13 coulomb, negative 13 coulombs. Then this is your nice, easy 3 marks. 1 for the formula, 1 for the substitution of everything, then 1 for the final answer. So now let's look into 422. Is just now plus, that is very key, 8 multiplied by 10 to negative 13 coulombs. This is how now the marks are being allocated. You get a 1 for saying it's a plus and a 1 for the value. Hence it's now 2 marks, and the other one is 3 marks. Hence that question at 4.2 is 2 marks. Tenulo, your answer is not right. I think Muso got it right. Now 0.6. I will also check again. So this is how we will mark this. We cannot give you 2 marks for just writing the value. Hence it said 2 marks, write down the net charge on sphere M after separation. But remember, M is the one that is now giving off the electrons. So M will now remain more positive. So it's basic things that we spoke about when we're explaining charge transfer. So 4.3 is an easy definition. Then 4.4, that is where I want us to go. At 4.4, the question clearly says, now calculate the net electric field at point P due to M and N. So it basically says we need now to draw a free body diagram. If you don't draw a free body diagram, you are going to end up now with a lot and lots and lots of mistakes. So I'm going to have my P here. And then I know that M is positive. Must maybe highlight it also. I know that M is positive, N is negative, such that I don't make now a mistake of using the incorrect science. So basically it says if this is P, then the influence of N on P is going to be attraction. So it means P will move towards the left. And because M is positive, so it means between M and P, I am going to have repulsion. And now confirm and check the distance thereof. The distance now between M and P is now 25 centimeters. The distance between N and P is now 10 centimeters. So I'm going to finish off this one quickly so that we also stay on time. So this will be P. So this will be P. So I'm going to have this here, and this will be now the E of MP, and then I'm going to have this one should be longer, E of N on P. Then it's easy to say E of NP is just KQ over R squared. That is now 9 multiplied by 10 to power 9. And then what is the charge on N? No, it is now 8 multiplied by 10 to negative 13. And what is the distance between N and P is 0.1 squared. And then we get our final answer as 0.72 Newton per coulomb. Then we do the same for E of MP, which is equals to KQ over R squared. And this is 9 multiplied by 10 to power 9. And now we have 8 multiplied by 10 to power 13. And then the distance now between M and P is 25. 15 plus 10 is 25. 25 divided by 100 is 0.25 squared. And then you get your final answer as something like 0.12 Newton per coulomb. So E net will just be E of NP plus now E of MP, and choosing now the direction to the right as positive, then I'm in a position of saying, okay, fine, I have now negative 0.72 plus now 0.12. This is the reason why we need now to specify in terms of the direction. This is the reason why we said in electric field is a vector quantity. So the final answer there will be something like negative 0.6 Newton per Coulomb. Newton per Coulomb. But now remember, we must not leave our answer as negative. Negative is 0.60 Newton per Coulomb, and the direction now to the left. And I hope everything was clear and straightforward in terms of explaining fully how to approach this type of questions. So what is key here was us having to draw the correct free body diagram. After the free body diagram, use now this equation once, because the direction is given, and now also be in a position of knowing and choosing the correct direction thereof. So if you check, this becomes easy. If you check, this becomes a normal routine of answering the questions. So remember, we only used now for 4.1, calculating the electrons. 4.2, we used now charge quantization. But now for answering it fully in terms of 2 marks, we needed to indicate that it is positive. So it is exactly 20:33. So it means we are 3 minutes after our closing time. So I'm going to allow you to leave your comments or inputs for the purpose of reporting into the chat. And maybe I'm going to allow just one person to say something. Kindly raise your hand if there's something that you want to say, any message or any question. But preferably it will be nice if I can maybe get a feedback of how the lesson was. Fumane Mashiani, your hand is up. How can we help you?
Sir, I just wanted to ask at 4.2, so when they tell us that electrons were transferred from M to N, does that mean like even after they touch and even after the electrons are transferred, the charges are still going to be identical?
100%. Remember, it's charge quantization. So it means now the charges are going to be identical. But in this case, because they are telling us they are moving from M to N, it basically tells us that M now is going to be more positive. That's what I said. When you are losing electrons, you become more positive. But if you are gaining electrons, in this case, N is gaining, it becomes now more negative. Hence, we got it as negative. So kindly be on the lookout for that. Thank you, Fumani. Jerry? We cannot hear you, Jerry. Your voice is very low, or it's either your mic. We can't hear you, Jerry. Come closer to the mic. Now you can talk.
After separation, now have
It's your network is somehow bad. We cannot hear you, Jerry. Kindly type it in the chat. I will attend to it, because now I can not hear you. And then Rilebuele is asking, evening, sir, regarding the camp, will the accommodation be provided? Rilebuile, 100%. The accommodation will be provided to you. Don't worry about that. That is covered and handled. All you need to do is to bring yourself and everything that is maths and science related, and the textbooks you have. Thank you. Ntabiseng Shabalala.
Sir, ne kopa ho botsa man mine calculator electric field ya which one ya 4.4 ntate ya NP. Ho 0.72 should we put the negative charge since 100 kata ho etsa the E net re entse be negative?
It's fine, you can do it the same that way. I don't have a problem at all, and they will still accept, but we'll give now the final mark for the left of the E net. I get the question wanted E net. Yes,
okay,
but if you do it in the multi-steps, I don't have a problem at all. It's even better if you do it that way, because we know now when you substitute it here, it must be negative.
Kopa ho fetisa molaetsa fela ntate.
Okay, me.
Ne ke re fela all the best with your June exams. Hope you write well and re tla kopana campong.
100%. Thank you very much. But we still have another session next week, which is the last one.
Okay, that.
Thank you. Okay, I don't see any other hands. Let me check the chat. Everything is nice and clean. So guys, I'm waiting for you to write your comments about today's session. And I will be now in a position of closing the session. So I'm going to give you a minute just to allow you to write your comments and everything. Then after that, I know everything is fine and sorted. I can see Mr. Villagaz Marshall is saying it was a great sir. Thank you so much. More comments, guys. I need now to report on this. If I'm not doing well, kindly tell me so that I can be able to improve moving forward.